Okay, so you saw the video and you saw how the shells kind of rotate around the axis of rotation. And the key is that they are nested inside of each other. They're kind of like those Russian nesting dolls, if you've ever seen them. So this is kind of looking at a slice um, of a bunch of shells. So you can see like this blue is only half the shell. We have another half, but see how the shells are all nested inside each other. This picture right here gives another perspective of the shells. Again, like we don't see all of the shells. It's kind of cut up so you can look inside and see what's happening, but see how the shells are nested inside each other. And so that's one big difference of the shells. So now we get an idea of just how the shells work and how they nest inside each other and how they can fill in the volume of revolution. In order to be able to use this, we need to find a formula for the volume of a shell. So let's look at that. So here's a shell. I kind of made it super thick just so we could label stuff in it. But you may be thinking, well, wait a minute. A shell is just a cylinder with another cylinder taken out of it. You're not wrong. That's exactly what it is. So the shell is the volume of the big cylinder minus the volume of the little cylinder. And if I make my outer radius capital R, my inner radius little r, we get this formula here, which there is pi and an h in each term. I can go ahead and factor that out, and I get this. But, that looks like the formula for a washer that we used before. And again, you're not wrong. It is the formula for the washer. However, we're not done yet. So we're still developing the formula for a shell. But this is getting here as part of the step. So the key is this. Remember how the shell is made. We have this representative rectangle that rotates around. The thickness of the representative rectangle is what tells us if it's a dx or a dy problem. And in this case, the way it's oriented, that would make this a dx problem. I need a dx in my formula. And right now, the thickness of the shell is nowhere to be found in this formula. If I'm not going to get a delta x, I can't turn this into a dx and get my integral. So I have to play around with this a little bit to get this dx in there. Okay, so what are we going to do? Just for ease, I'm going to go ahead and call delta x w. And if delta x is w, representing the width or the thickness of the shell, I'm also going to introduce something else. I'm going to introduce p. P is the average of the radii, which you can always find by adding the two radii and dividing by 2. In the picture, though, that means P would start at the center and go halfway between big R and little r. So it's exactly halfway through the thickness of the shell. And if that's true, then I can create these two equations for the outer radius and the inner radius. The outer radius is P plus half the thickness, and the inner radius is P minus half the thickness. And that's exactly what we've got here. So now I'm going to go back to this equation that we had, and I'm going to substitute in for capital R, P plus half the thickness, and for little r, P minus half the thickness. Now it gets a little messy, but it cleans up really nicely. I square this, and that's where this comes from. I square this, and that's where all of this comes from. P squared minus P squared that cancels out. W squared over 4 minus W squared over 4 cancels out. And I just have PW minus negative PW is 2PW. And I just realized I need another set of parentheses here. Let me just put that in real quick. And then I have my pi and my h. So you can see the formula simplifies down very nicely. And now we have a formula that has w in it, which is the same thing as delta x. And I get my formula for the volume of a shell. So it's 2 pi. P is really the radius of the shell, h dx. And here I talk about that. Remember how we're going to fit more and more shells in order to get a better and better and better approximation for the volume. The more shells we fit in, the thinner this rectangle gets until we have an infinite number of shells, which means this becomes infinitely thin. And when it becomes infinitely thin, the outer radius, the inner radius, and P all essentially end up being equal to each other. And so let's just call P the radius of the shell. 2 pi radius times the height times the width, where width is going to be the thickness of the shell, the dx or dy. So the volume for one shell is 2 pi RH times dx. The volume of the solid then is approximately the sum of all the volumes of the shells. If I have an infinite number of them, we get the actual volume of the solid. And then at that point, we can change it to a definite integral. And finally, we get the formula for the volume of a shell. Whew. So this is what we'll use to find the volume of revolution by the shell method. And remember, this time, the representative rectangle is parallel to the axis of rotation. So if it's parallel and your axis of rotation goes vertical, then the representative rectangle will also go vertical. This is where you would measure the radius, the distance from the axis of rotation to the rectangle, and the length of the rectangle would be your height. Even if it's going horizontally, your rectangle would go horizontally, but your radius still goes from the axis of rotation to the rectangle, and your height is still the length of the rectangle. And notice, by the way, that means you're always going to have either the radius or the height vertical, and then the other one goes the other way. Radius is horizontal, height is vertical, or radius is vertical, height is horizontal. So you actually are going to have a mixture of right minus left and top minus bottom when you're putting your equation together here. All right, so we're going to go ahead and stop this video there, and then I've got some examples for you coming up.